In case of differential equation of higher order, linear differential equation with constant coefficient, we initiate with the simple example of d2y dx2 plus a dy dx plus by is equal to fx, where a and b are constant. Constant coefficient. So for this type of linear differential equation of order 2 or more, we replace y with e to the power mx as a trial solution. This is because all the functions in mathematics, more or less, cosine function, sine function, cosine hyperbolic, sine hyperbolic, log function, everything may be obtained with linear combination of this e to the power mx form. And if we differentiate y equal to e to the power mx once or twice, what it becomes? It becomes nothing but e to the power mx m square plus am plus b, and you take the right hand side to be 0, because this is going to give us the general solution, not a particular integral. And if we take this as an operator, d2 plus ad plus b, which when operated on y gives fx, we can find the particular integral yp as 1 upon d square plus ad plus b operated on fx. So we try to solve this equation in two ways. First, we take the right hand side 0. This is called homogeneous form, where right hand side is always 0, and we give the trial solution e to the power mx as y, and this makes the general form transform to this. And we all know that e to the power mx is 0 only when x tends to minus infinity. So this is not 0, and we have this equal to 0, which is termed as auxiliary equation. And from this auxiliary equation we get the values of m, which gives us the general solutions as written linear combination. If it's a second order equation, we have two values of m, and we write the general solution as c1 e to the power m1x plus c2 e to the power m2x. This is called complementary function, and we get the general solution as y equal to this complementary function plus this particular integral of this equation. So we tend to solve this equation in two ways. Whenever a higher order, this is a second order equation, if it's third order or fourth order, we can follow the same procedure. So first we get this term to be 0, accept it to be 0, and give it a try with the trial solution to the power mx, which gives us this auxiliary equation, from which, if it is a third order equation, we have cubic equation as auxiliary equation. If it is a fourth order equation, we have biquadratic equation as auxiliary equation, as you can easily follow. Now we have illustrated it with a simple example of second order differential equation. And in case of second order differential equation, we have a quadratic which has two roots m1 and m2 of m, And for that we have two trial solutions, y equal to e to the power m1 mx and y equal to e to the power m2 mx, and we take the linear combination of them to be the complementary function yc. This is termed as complementary function because we have complemented the right hand side with 0. And when you take fx to be here and find a particular solution, here we have used this as an operator. D stands for ddx, as you can easily follow. So this is d square, this is ad, and this is b, and we are inversing this operator. We find the particular integral. So how can we find the particular integral? Let us illustrate with an example. Let us take the equation of second order, and we have here e to the power small x. Okay, e to the power small x, and we assume that this equation or this operator may be factored as okay. So what will be the particular integral? It will be like this. Isn't it so? So to find the value of particular integral, we would like to illustrate that if we write this equation as, the operator fd operating on y giving e to the power x, then yp is nothing but fd inverse operated on e to the power x, or 1 by fd operated on e to the power x. And we claim that this yp can be written as simply as this if fa is not equal to 0. And if fa is equal to 0, that means that this fd has a as a factor, and in that case we change this formula as 1 upon fd operated on e to the power x gives us e to the power ax into 1 upon f d plus a operated on 1. Since e to the power x can easily be written as this, this is taken as a constant function of x. Let us illustrate on this rule. This rule is more or less simple to find. Just take fd as d square plus ad plus b. As we know, the equation is written as fd operated on y is equal to e to the power x. Isn't it so? It's okay. I think where a and b are constant. Now, what is d? We know that d is d dx. So what is d square plus ad plus b operated on e to the power x? Obviously, if we take two derivative of e to the power x, it becomes a square e to the power x. And if we take single derivative of e to the power x, it becomes a e to the power x. And this is b to the power x. Isn't it so? So this can be written as a square plus aa plus b into e to the power x. Now what is ft? So we replace d with a here. A square plus a into a plus b. So this is nothing but fa into e to the power x. Isn't it so? So fd into e to the power x gives fa into e to the power x. So obviously we can claim that 1 by fd into e to the power x is 1 by fa into e to the power x. Isn't it so? So this is very simple. But we cannot apply this formula if fa is 0. Now when is fa 0? Fa is 0 when this quadratic has a root a. That means this fd has a root same as this small a. So in that case, we apply this formula that if fd is operated on e to the power x into v, we have a formula like this. And from here we can find that actually this should be written as this. Whenever d minus a is e to the power x v, e to the power x 1 upon f of d minus a, sorry, d plus a operated on b. Now how does it happen? Let us illustrate. Let us similarly take d square plus let us take d square plus ad plus b operated on e to the power x into v. Here v is any function of x. So what does it become? It becomes, what is d of e to the power x into v? It is nothing but a e to the power x into v plus e to the power x into d of v. So it may be written as e to the power x into d plus a operated on v. Similarly, if we get d square e to the power x into v, we get d square e to the power x v means derivative of this term, and we get a square e to the power x into v plus a e to the power x into dv. Here also we have a e to the power x into dv, makes it 2 into a e to the power x into dv plus e to the power x into d2v. I think it is clear, because d2 e to the power x v is derivative of this term. So when we derive this with respect to x, we get a square e to the power x, v remains constant, and then a e to the power x dv. And here when we derive e to the power x, we get a e to the power x into dv. So they add up and gives 2a e to the power x into dv. And e to the power x is kept constant, then d2v comes out. So this can be easily be written as e to the power x, if taken common, this is d plus a whole square into v. Isn't it so? So if we apply these two here, this becomes, see, d square e to the power x b, it becomes e to the power x d plus a whole square into v plus a into d of e to the power x b gives e to the power x into d plus a v, and lastly we have b e to the power x into v. So we can write it as, this is equal to, we take e to the power x, e to the power x, e to the power x common, and we have, what we have, d plus a whole square plus a into d plus a plus b, and that is operated on v. Isn't it so? Remember that this is an operator, so we can easily replace it as e to the power x into f of d plus a. Since this, if this is fd, so obviously if this is fd, obviously this is f of d plus a operated on v. And from this relation we can easily claim that 1 by fd operated on e to the power x into v gives e to the power x into 1 upon f of d plus a operated on v, where v is any function of x. So I hope this is explained. This term is dv. Sorry, 1 upon f of d plus a operated on v. Because from here what we have fd operated on e to the power xv is nothing but this. Okay, and if we let me explain it a bit more. This we can write it as e to the power x into, let us write it as v1. So what is 1 upon fd operated on e to the power x into v1? It is nothing but, in the left hand side we have e to the power x into v. Now since f of d plus a into v is v1, so this is nothing but e to the power x into 1 upon f of d plus a operated on v. Isn't it so? F of d plus a operated on v is v1. So 1 by f of d plus a v1 is nothing but v. So we have this relation, and v is a function of x, so v1 is also another function of x. Another very important procedure of finding particular integral in case of differential equation where the right hand side has function like cos x, or we may say sin x, is that if the differential equation is like this, we can at once write yp as phi d by f1 d square operated on cos x or sin x, whatever you write. In both the cases we have same result. This gives phi d by f1 minus of a square cos x or sin. Okay, now how does it happen? We have multiplied with a new function phi d, and this fd becomes f1 d square, and then we replace d square by minus of a square. Let us explain it with a specific example. Why this becomes so? This becomes so because whenever we have d of cos x, it is minus a sin x, and whenever you have d square cos x, that means we have d of minus a sin x, and this becomes minus a square cos x. So you see, if you replace here cos x with sin x, you get the same result, because d square sin x is first a cos x and then minus a square sin x. So whenever we have cos x or sin x, d square is always replaced by minus of a square. And so whenever we have this type of differential equation, yp gives this, and we multiply this fd with phi d, so that this becomes a function of d square only. How can you do that? It's a very simple way of rationalization. If we have d square minus 2d plus 4 operated on y equal to cos x, then yp is nothing but cos x operated upon d square minus 2d plus 4, and we multiply with d square plus 2d plus 4 of this cos x, and in the denominator it obviously becomes d square plus 4 whole square minus of 4d square, isn't it so? And we replace this d square by minus 1, so this becomes minus 1 plus 4 whole square minus 4 into minus 1. Remember that d square is replaced by minus a square, minus 1 here. And in the numerator we have d square plus 2d plus 4 operated on cos x, which can easily be evaluated. D square of cos x is nothing but minus cos x, plus 4 cos x gives it 3 cos x, and 2d of cos x gives minus 2 sin x. So we can easily write it as 3 cos x minus 2 sin x by, this becomes 3 square is 9 plus 4 is 30. So this is an illustration.